All right, so yesterday we did future value annuities. So I want you to imagine something like an account that you're putting money into. So we did a lot of investment type questions where you're doing some kind of investment plan. Um, Present value annuity would be a sum that you need in order to take regular payments out of it. So for instance, if you've saved up all your life in a retirement savings plan, and then eventually you need to start taking regular payments out of that. This formula would be for that. Another example would be something like a mortgage. So you get a lump sum loan, and then you have to make regular payments to pay that off. So in the first scenario that we learned about, you're putting payments into something, and you're gaining money in some way, so like an investment or savings plan or something like that. In this case, you have a lump sum already and you're taking money out of it, or you're trying to pay down some kind of loan or something. All right, so we have a rearranged formula for present value, and it is the PV formula. So you'll see the FV formula, which is yesterday's, which is future value, and the PV formula, which is present value. So PV represents present value of the annuity in dollars. Okay, and R is going to be the same as it was before, which is the regular payment. So my mortgage payment, for instance, would be my regular payment, and the present value right now is how much is remaining for me to pay down on my mortgage, basically. So the regular payment is also in dollars. And I just want you to remember that in these cases, R over CP, where R is the interest rate as a decimal and CP is number of compounds per year, is typically represented by I, which is essentially just the division of these two things. And then negative CP times T in this formula is typically represented by negative N. So it just represents the total number of compounds in the total time that you have. Okay, and then same thing down here, that is typically represented by I. But we just break it down to make it a little bit easier to locate all the information and plug it into the formula. Okay, so these formulas will be given to you on your test and on your exam. You don't have to memorize them, you just need to know kind of like what the variables represent. Okay, same as yesterday, this formula can only be used if the payment interval matches the compounding period. So if the interest is compounded every month, the payment would be taken out every month, or if I'm paying my mortgage, I would be paying it monthly, basically. Okay, so let's look at a couple examples here. Victor wants to withdraw $700 at the end of each month for 8 months, starting 1 month from now. His bank account earns 5.4% interest per year, compounded monthly. How much must Victor deposit in his bank account today to pay for the withdrawals? So the idea is that you're gaining interest on that, even though you're making some withdrawals from that. Okay, so let's write out our variables here. We have PV, we have R. We need little r as well. There's big R and little r. We have CP, and we have T, which is time in years. So what things do we know from the question? Okay, so that will be lowercase r, 0.04. Just divide this by 100. Okay, what else? Okay, because it's compounded monthly. Perfect. Okay, what else? Yep. So this should be like when we do time here, this should be time in years. So we need to figure out 8 months. If this is compounded monthly, we would have really just compounded like our interest 8 times, right? So when we do the calculation, T, because this is in months, needs to be divided by the number of months in a year. So 8 months over 12 months. So what do we get for that? Okay. Or we just leave it as 2/3 because that's a repeating decimal. So let's leave it as 2/3 of a year for this one. So 2/3. Okay, and then do we know the regular monthly amount that's being withdrawn from the account? Or do we know the total that's in the account? Okay, so 700 we know. And then the amount that he needs in order to fund these withdrawals in the account is unknown, so that's PB. All right, so let's calculate with the formula. So just as a reminder, this is what our formula is. Make sure you have your brackets in the correct spots. All right, so plugging everything in, this is what we should have. One calculation that you might want to do would be these fraction calculations and exponent calculations before you actually put the whole thing in your calculator. So we'll do one extra simplification step. Gabe, if you feel confident that you can put this in your calculator right away, then you can do that while I do these ones. Okay, and if you're watching the lesson video, you can pause and try this calculation on your calculator.
Okay, so if you did it correctly, we should end up with a present value of $5,480 and 28 cents as the present value that's needed in that account. So when we think about actually like how much he's taking out $700 for 8 months. So if you do 700 times 8, you actually get 5,600. So why does he only need $5,488 in the account if he's actually taking out 5,600? What's the reason for the difference there? What's the point of him even putting this money into the account in the first place? Like, why is he putting money in and then, like, slowly taking money out? Okay, so then you need less money than what you actually need, right? Because you're gaining interest on that by having it in that savings account over time, right? So although by the end he's taking out 5,600, he only needs 5,488 initially in the accounts. Some of that's going to earn interest over time as well. Make sense? Okay, so therefore, what would you say for this question? So that's what he's putting in at the beginning. He puts that in, and then he's gonna slowly take it out. Yeah, yeah, perfect. So for right now, we'll say Victor should put $5,488.28 into the account to finance his withdrawals. Okay, perfect. Let's try another one. Zeta plans to retire at age 60. She would like to have enough money saved in her retirement account so that she can withdraw 7,500 every 3 months for 25 years, starting 3 months after she retires. How much must Zeta deposit at retirement at 9% per year compounded quarterly to provide for the annuity? Okay, so let's list out our values as usual. That's where we're always going to start. Interest rate is a decimal. CPT, which is time in years. And I think that's everything, right? Okay, what do we know? Yep, perfect. Perfect. So PV is so I'm not going to rewrite the formula again. We'll just use obviously have it written up here. We'll just use that again. Okay, and then I'm just going to do one extra simplification step. But if you feel good about entering that into your calculator, you can. So this is 1.025. And if you're watching the lesson video, you can just pause and do your own calculation on your calculator. Alright, you should have gotten $297,313.05 for your present value in the account. And then, Gabe, can you give us a therefore sentence? Yeah, great. Yeah, sorry not to say but to withdraw 7,500 every 3 months for 25 years. Okay, perfect. the last question, and we can just do this self-directed part here. So we'll end it